programs.
Great. Thank you. Yes, so my name is Sam Westrick. I'm a student at Carnegie Mellon University, advised by Motakar. And the property I'd like to tell you about today is a property we've kind of discovered organically out of nested parallel programs, and it's a structural property relating the role of effects and the structure of memory in your program. So let me talk a little bit about parallel programming. Historically, there's been somewhat of a dichotomy in your approach to parallel programming, say a functional imperative dichotomy, where on one side that you might approach your problem with the expectation that you'll be using primarily immutable data. Maybe you'll have a language that uses automatic memory management, say automatic GC. And maybe it's you have some goal of, say, determinism or something like this. So that'd be like the functional side. And on the other side, you might instead approach your problem from an imperative perspective of saying, I want in-place updates, I want mutability. I want, say, manual memory management in order to more carefully control where my memory is and when it gets allocated, when it gets freed. And perhaps then you are plagued by problems of, say, non-determinism, data races, and these sorts of things because of some of those choices. With this dichotomy, there comes a question. Okay, some people, or in general, some of these characteristics of, say, functional programming are associated with a lack of performance. And a lot of these characteristics of imperative programming are associated with some sort of fast performance. And this is the question that we're really trying to get at in this work. We're trying to understand, is this really true? And the question we're really trying to answer is, can parallel functional programming be fast and scalable? When I say fast, I mean competitive with the fastest techniques that you might have available to you in, say, C or C++. That's the goal that we have in mind. Okay. Now, a lot of people have worked on this problem, and all of them end up kind of solving the same problem or trying to work on the same problem, and that is memory management. Everybody ends up working on GC. Okay. So why is that? Well, in the sequential world, the story is like very simple. You have a shared resource, your memory, and you have a mutator on one side and a collector on the other side. And I like to think of the mutator and collector as just two concurrent processes that are both accessing the memory at the same time, and they coordinate in some clever way. Now, why is it harder in the parallel context? Well, the memory is a shared resource, and suddenly you have a lot more mutators all hungry for a little bit of access to the memory. And a lot of the traditional techniques for garbage collection don't perceive any sort of structure to the memory. And so the best way we can design an automatic memory management system is to just kind of shove a bunch more collectors in there too and hope for the best. And so the question we're trying to ask is there a better way? And a lot of people have begun realizing that actually functional programs, but really programs in general, have a lot of structure to them in the memory and elsewhere. And that's what I'd like to talk about today. So there's a particular structural sort of design choice, algorithmic design choice that has been like a classic and popular approach for many, many years. It's called nested parallelism, or you might have heard of fork-join parallelism. Okay. There's tons of examples of this. It goes back to multi-Lisp, or perhaps even before that, and more like recent examples, even in Rust, there's a library called Rayon that you can play with. In Java, things like fork-join, Habanero, X10. In C and C++, you have access to things like OpenMP, Silk, the thread building blocks, so on and so forth. In some of the more functional categories, we have lots of dialects of parallel Haskell. We have Futark, we have the Manticore project, and I'll actually be talking today about parallel ML. So what is nested parallelism? It's a really simple idea. You have threads that can dynamically spawn other threads and synchronize with them, but it has to obey a particular structure where if you fork off child threads, you have to wait for the child threads to complete before you can synchronize with them. And this internal thread is really suspended while the children are executing. We call it nested parallel because this can happen anywhere. So if you spawn a thread, that thread may run in parallel or it may not. It's up to the choice of the implementation. And that can sort of recursively happen to create a dynamic tree. So just a little example to kind of give you a glimpse of what I'm imagining here. We are going to be like thinking about parallel ML. And so you can imagine there's kind of two interesting things that we might care about in the code that we're working with. First of all, we are not purely functional. We are going to permit mutation. And that's really crucial for efficiency. We have not been able to doing strictly immutable data, we've not been able to compete with low-level techniques. And we have this nested parallelism. So you can see that here in this example where we have that double bars notation that just means run these two expressions at the same time. And we can see this nested parallelism in the sense that these expressions are themselves recursive calls that have parallelism in them, right? If we were to say, oh, by the way, this is a computation just doing a map on an array. Okay, and this is actually a highly efficient in practice implementation. Now, if you were going to run this, say, on an array of size 4, what would that look like? Well, initially you have a single thread that calls map, and now the first thing it's going to do is it's going to spawn 2 children. You know, we're going to start partitioning the array up into segments, and those are going to spawn 2 children. Okay, now if the array was size 4, we're down to the base cases. Now we actually get to do the write to the output array at each of those 4 threads, and then the whole thing joins back up, and then our computation is complete. So now I'd like to define this property, disentanglement, for you. This is the focus of this work. And the definition is very simple. We want this property throughout execution. Each thread is going to be restricted in what sorts of other data it can use in its computation. So specifically, we restrict threads to data allocated either by itself or by ancestors. Okay. So if we were to look at this leaf thread here, it's only permitted to access this root to leaf path. And so, for example, it's permitted to access this data allocated before it at the root. It's permitted to access this data here, but it's not permitted to access something at a cousin or a sibling or something like that. And this red arrow is what we call entanglement. So that's where the name comes from. And another example, this leaf thread over here is only permitted to access its root to leaf path. Okay, so this might seem like a strange property. You might be wondering, why is this relevant? What does this have to do with memory management? And how does it fit into what I'm already familiar with? So one of the things we address in the paper is figuring out how it fits in. So it actually goes approximately here. This is disentangled computations. Okay, so there are ways to not be disentangled. Of course, if you can share memory between threads, then you can violate this property. So it's not fully general. But it is actually, it turns out, more general than race freedom. So one of the theorems we prove in the paper actually is that all race-free programs are disentangled. And this is part of the reason why we've noticed that this property emerges naturally out in the wild. The proof is a little bit interesting. We actually had to define things in a slightly different way than what I've shown you so far. We had to identify this tricky single-step invariant. You have a concurrent program with non-deterministic stepping, and you need some sort of single-step invariant. Well, that was our proof technique, at least. And the idea is basically that the one-hop neighbors of memory locations are always in your root to leaf path, if an access there would be okay for race freedom. And then we can carry that invariant through the proof. Now, disentanglement practice. So as I mentioned, this property actually, we discovered this property organically by just inspecting real-world code. So we considered 2 different benchmark suites, actually. One called Ligra and one called PBBS. Well, Ligra is a framework for graph programming. And both of these are generally considered to be some of the best multi-core parallel codes that you can find, like a shared memory multi-core sort of parallelism out in the world. Okay, all of these are disentangled. And by the way, all of these are written in C, C++. This is really something which is applicable to really any language. Now, there's another thing that we found interesting, looking at all these codes. There's lots of examples that use data races in a benign way. For efficiency reasons, actually. It can be very beneficial to use data races. Okay. So we actually see this disentanglement property as something which is interesting, perhaps even as perceived as a correctness condition. Race freedom is a very traditional correctness condition for parallel programming, but actually in practice what we're seeing is that people use races all the time. And they use them in ways that they understand and actually can utilize for improved performance. So perhaps there is a sweet spot between data races and between fully general programming, and perhaps disentanglement is one of those options. Okay, so I've defined this property for you. How can we utilize this property? Let's get back to this question of memory management. Is there a better way than just doing this? Well, nested parallelism gives us a structure to our mutators in our program. And disentanglement gives us a structure to the memory that they allocate. So the idea is that actually the shared memory that our program is using is not just this completely unstructured mess. Actually, really, it has sort of a tree structure to it. and we could take advantage of that. So what I'd like to do now is explain this technique that we're using in an implementation called hierarchical memory management. It's a really simple idea. We're going to take our threads in our program, and we're just going to give them thread local heaps. On a fork, we have to initialize the new children with fresh empty heaps. And when synchronization happens, we merge the heaps up. Because we're talking about heap allocated data here, it's not like stack allocation. The stuff that the children allocate actually really gets returns to the parent. Disentanglement gives us a really nice property of no cross pointers. If you look at the memory graph of your program, like what objects are allocated in that heap and what objects are allocated in that heap, they cannot point across. They can only point up and down. Okay. And this gives us access to a technique that we call subtree collection. You can pick a subtree of this hierarchy, and you can do garbage collection just in that subtree without interfering with the program elsewhere. Okay. You can do really whatever you'd like inside the subtree. You can apply any existing GC algorithm inside the subtree, for example, to do collection. Another thing that's really cool about this is that it's naturally parallel. Two non-overlapping subtrees can be collected at the same time, and they really do not interfere with one another at all. For a big example, actually in practice, this hierarchy of heaps can get quite large. Because, for example, we're running on large multi-core machines to do testing. Maybe we have 64, 72 processors, something like this, even maybe into the hundreds. And you can have many of these garbage collections happening in parallel, all at the same time, with different scopes. And so a really interesting design question for the future is how to design a good garbage collection algorithm to handle this sort of flexibility, where you can choose any subtree, really, to do a collection on. So we've taken this idea and implemented it. So we wrote a compiler. Well, we extended Milton. So this is the full ML language. It's standard ML, fully featured standard ML. We've added one thing to it. We've added this par function, which takes two thunks as argument and runs them in parallel. And it returns their results. This thing is quite stable now. It's actually in use by about 500 students every year at Carnegie Mellon University. We're using it in an undergraduate course to teach parallel algorithms. And our experience is that students can, within a month, be writing actually quite fast parallel code without actually having to think about mutation at all. This is something interesting that we've been doing where you can imagine I give a student a parallel sequences library. I write all the nasty code under the hood that does fancy mutation and whatever. But from the perspective of the student, they just use a pure function, map on an array or reduce on an array or something like this. And so they can compose these things and actually get really good performance. Underneath the hood, what's going on is disentanglement, parallel collections, and all this stuff, but the student doesn't even need to know about that. So as I said, we extended Milton. We had to rewrite the runtime system, and one of the interesting challenges here was writing the GC, of course, is the interesting challenge here, right? How to get subtree collection integrated with the scheduler. And that's actually a really interesting topic, and I'd love to talk to anybody about that afterwards, if you're interested as well. Please go download it and play with it and submit bug reports. We did some experiments. So we took some of those benchmarks in Ligra, in PBBS, and ported them to parallel ML. And so this first experiment is just to look at scalability, and we're comparing against sequential Milton as our baseline. So we take the sequential elision of the same program and use that as our baseline. The one thing I want to mention here is that if you were to run the exact same sort of benchmarks in PBBS using C or C++, you would see similar curves, okay? That some benchmarks just don't scale as well as others, but the point to take away here is that actually the sort of scalability we're getting is similar to C and C++. But now you might have a question about absolute efficiency. Are we actually fast? Maybe our baseline is too slow. Turns out Milton is actually very fast, right, as a baseline. Milton generates excellent code. But I do have some real experiments to back this up as well. We did a sorting shootout. We collected some of the fastest sorting codes that we could find in different languages. And actually, our Maple implementation, which is a merge sort, is the second fastest that we found so far, only behind Silk. And Silk is C, C++. Silk is the runtime for nested parallel C and C++. So just to wrap up, this disentanglement property we're really excited about because we think that it is something which is everywhere already. We have evidence that it is everywhere already. We think it's applicable to all sorts of languages. You could plug this into Java probably. If you have some, I don't know, deterministic parallel Java or something like this, and you could plug it in. Any sort of type system that guarantees race freedom. This is definitely applicable to Rust, even though Rust already has its own memory management story. But like any sort of system that guarantees race freedom, you should be able to plug this in and get some of its advantages. I posed this question for you. That we're really curious about. Is disentanglement an interesting correctness condition instead of, say, race freedom? Maybe we'd like to think about how races are actually being utilized rather than how we can rule them out. And some future work we'd like to look into is some static and dynamic checking for disentanglement. We have a little bit of progress on this already, and I'd also enjoy chatting with you about that after, if you're curious. I talked about this hierarchical memory management property, parallel collection, and this Maple implementation, and pretty please go download Maple and play with it and let us know what you think. So, thank you.
Any questions?
So what happens when I just write an entangled program in Parallel-ML?
Good, yeah, so right now we do not have checking implemented yet in Maple. So it possibly will crash in the current implementation. And that's why we're working on this static and dynamic checking as the next thing.
Hi, great talk. So my question is, how would your work compare with work like Multi-Milton, which does have thread local heaps, and you have parallel collection on all these local heaps, and it just uses a shared heap for the communication between them?
Yeah, so there's a couple differences with some of these other projects. Multi-Milton had much more emphasis on concurrency rather than parallelism. Actually, a lot of the benchmarks that we're kind of talking about here and have in mind here are trying to avoid concurrency as much as possible for efficiency reasons. The Multi-Milton project also had a kind of a completely different perspective on the GC thing. One of the goals of this project was to identify a concrete property that we believe we could assume about all input programs and take advantage of it.
This disentangled parallelism looks exactly like the programming style with Go routines of the Go programming language. It's not exactly enforced like that, but it's the preferred and promoted style. Can you comment on this?
Yeah, so I still need to learn more about Go. My understanding with Go is that essentially you have channels, is that right, between Go routines that you can communicate over. And so they do have essentially communication with concurrent processes, whereas to some degree disentanglement is disallowing that. Now there's some caveats there. If you sort of pre-allocate things with disentanglements, then you can do races, and that's one of the cool things that we noticed with this thing. So anyway, we're actually interested in incorporating some sort of message passing into say a disentangled system and seeing how it can coexist.
Great talk. Thanks a lot. Here. Hi. I was interested in seeing the performance comparison with the other benchmarks. We only saw merge sort, and in particular those that have benign data races for performance. Can you say something about the performance there? How does it compare?
Oh, good. So yeah, we're in the process of doing a more thorough evaluation between, say, C and C++ and this implementation. Across the board, what we're noticing is generally we're within a factor 2 or 3 of C and C++. That's pretty much across the board from all the things that we've looked at so far. We've looked at a variety of Ligra benchmarks as well, and yeah, we're getting fairly good performance.
Hi, great talk. What does the per thread overhead look like?
Sorry, can you say it again?
What does the per thread overhead look like for the additional heap and whatnot,
Oh,
the
good,
accounting
good.
you're doing?
Right, so one of the implementation tricks that was crucial for this implementation was to make sure that we only create new heaps when you actually have a physical migration that happens in the scheduler. So you don't create a new heap every time there's an opportunity for parallelism. You only create a new heap when there actually is physically a parallelism created by a steal, say in the work stealing scheduler. So that was very crucial. Basically, in the implementation, the way we expose parallelism is you actually just you put a thunk in an array, and then somebody else can take that thunk. But when they do, they have to create a new thread for it, create a new heap for it.
What was the overhead?
Like measured. Sorry, you mean measuring the actual overhead itself? It's comparable to standard overheads for exposing parallelism in other languages. Actually, the overhead of creating a thread is actually much higher generally than the overhead of creating a heap. Heaps are actually very light data structures. It's you can think about them as linked lists of pages.
Okay, so that was related to my question. So merging heaps and do you see any fragmentation?
Good. So right. So the heap architecture. As I mentioned, heaps are essentially linked lists of pages. It's easy to argue at the very least that you get like at most a factor 2 of fragmentation because you're going to keep allocating inside the same page, and at a certain point you're going to see an object which is too large and you have to jump to the next page. But that'll give you at most a factor 2 off of the best that you can hope for. In general, the fragmentation is usually much less than that because the objects that you're allocating are small, and say a one page is 4K. Typical object maybe is like, I don't know, 64 bytes or I don't know, something like this. And so actually you get very good utilization within blocks.
Let's thank the speaker again.